I welcome you for this lecture of NPTEL on earthquake resistant design of foundations. And as you know that this course is in 5 modules, and right now we are working on second module, which is on shallow foundations, and this lecture is the last lecture on this module. And as we discussed in the last lecture, that under the shallow foundations, these are the components, general requirements, bearing capacity and settlement, combined footings, rough foundations, and finally we have already started to discuss on footings subjected to dynamic loads. So, today we are going to talk on the second lecture on footings subjected to dynamic loads, and then we will have in fact 2 more lectures on this footings which are subjected to dynamic loads. So, this will not be last lecture, but another 2 lectures, then only we will complete the shallow foundations. So, as we discussed in the last lectures that footings which are subjected to dynamic loads, we have already talked about dynamic loads and methods of analysis, and especially we have discussed pseudostatic analysis, earthquake loads where you have considered horizontal load and moment. And one of the important issue which comes during the dynamic load including the earthquake load also, that in addition to vertical load either some moment is acting or some horizontal thrust is acting. Particularly when a moment is acting, then the vertical load can be replaced by simply in another vertical load acting at some eccentricity, but without any moment. So, all these things we have already discussed in detail. For dealing eccentrically vertical loads, one simple method was given by Maheshwari, where you reduce the width of the footing by B prime equal to B minus 2 times of eccentricity. You may be, I think you recall my last lecture. Then but that method is not rational. Then a new method has been proposed by Prakash and Saran, which we have discussed in detail in the last lecture, where you have the effect of eccentricity in terms of ratio E by B on the bearing capacity factor NC, NQ, and N gamma. Okay. And at the same time we also discuss the effect of this eccentricity on settlement. So, all these things has been discussed in detail. What I am going to talk now today in this lecture is design procedure for this new method, and then we are going to talk about any design example also, and finally I will wind up this lecture using a case inclined load on a footing. That means not only it is subjected to vertical load, but it is subjected to a horizontal thrust also. So, let us talk first about design procedure for the new method. First of all, whenever you want to design anything in civil engineering, including the footing or foundation, you require data. So, what are the data which are required for this design? You require vertical load and moment and its eccentricity. So, out of this vertical load will be always Q will be always available. Now, the second data, whether it is given to you eccentricity or what we called the moment value. Then you require the properties of the soil, that is C phi, or if C phi is not given, at least what is expected, that is the SPT n values. Then beside that we should have some plate load test data, where you may have the load settlement curve using on the plate load test. So, that data will be used in the design. Then your this designers need to have the value that what should be your permissible value of settlement as maximum settlement, as well as tilt, how much you can apply. And finally, the factor of safety and your shear consideration. That means when you want to find the allowable bearing capacity or sap bearing capacity from ultimate bearing capacity, then what should be the factor of safety should be used. Normally the factor of safety, the last part is minimum value is 2.5 or 3, but when you design for earthquake loads, then it will be better to have some higher values. Now, what you have in this new method, what is the design procedure? The design process suggests that first one, select a trial dimension of the footing, and when we say dimension of the footing, that means normally width for rectangular footing, it means width of footing, and depth of the footing may be fixed from some other consideration. That means the depth of the footing, sometime what happens, you need to carry particular like that situation that up to certain depth you need to carry your footing. So, depth of the footing may be fixed from other consideration, but width of footing can be assumed. That is the first assumption for this procedure. Then for if moment and vertical load q is given, then calculate the value of eccentricity E, which is simply m by q, and then also find, once E is known, then find the ratio E by B, because B is already assumed. So, you can have E by B. Then compute the settlement for this given E by B values, and when you compute this settlement, naturally what you require for the settlement, first calculate the ratio S E by S naught and S m by S naught using equations 6a and 6b, which we have discussed just in last lecture. Compute the value of S naught from permissible value of S m, where S naught, once you know the value of this ratio, let us say that this ratio S m by S naught is known to you, okay? And if this ratio is known and S m is given to you, then you can calculate the value of S naught, and this S naught is nothing but your S f, as we discussed earlier also, that settlement of footing is same as settlement this S naught, and once settlement of footing is known, then settlement of plate S p can be calculated S p. Okay. Continue with this. Next steps are that what you require for design is plate load test data. Now, the issue is this, what you need to do with plate load test data. Plate load test data is normally what you get is load settlement curve in the plate load test, and using this load settlement curve, find the value of bearing pressure that correspond to settlement S p found in step 3. In step 3, you have determined the value of S p. Now, using this value of S p, find the value of bearing pressure coming that, okay. And using the load settlement curve, we also find the bearing pressure using what is the method called tangent method, and whatever the value of q b, which is lower in step A and for A and B, that should be further used. Okay. We will discuss one numerical example and then things will be very clear, do not worry about it. So, then what you have, that failure criteria of plate, what you can have, failure criteria of plate will be decided based on the shape of the plate load test curve. When you have this load settlement curve, depending on what we can say, it could be general shear failure or local shear failure. So, factor of the safety of the footing, what you need to have for the factor of safety, how it should be computed, compute ultimate bearing capacity Q naught for E by B equal to 0. That means, the value of, use the equation of Q d, which we have already discussed, but this should be used when the value of E by B equal to 0, and for that means neglecting the eccentricity, and for this value find the factor of safety simply using this equation, ratio of q d naught divided by q b. Okay. If this Fs which you are getting this ratio is greater than the required value of factor of safety, which is normally 3, then it is okay. If it is less than that, then naturally what we need to do, we need to go on step 1 and revise the design. If Fs is getting less than required value, then you need to increase the width of the footing. So, that means value of B need to be required to be increased. Okay. However, if you are satisfied with this factor of safety, then you can go ahead and then we continue with this. Then next step, let us say assume that factor of safety is adequate. In that case, we find the ultimate bearing capacity Q d of actual footing for given value of E by B. Naturally, this value of Q d is going to be less than Q d naught, where Q d naught was without eccentricity. So, that is understood. So, anyway, we find this value of U E by B and find the value of Q d. Then again we find the allowable bearing pressure using QD divided by the factor of safety which has been already fixed, and then once allowable load is known, multiply by the area of the footing, then you compute the allowable load, and this allowable load should be the more than the given load, then it is okay, otherwise you need to revise the design. Finally, assuming let us say step 7 is clear, then we check the tilt of the footing using equation 5, because SE and SM are known. So, you can calculate this value of tilt, and the value of tilt should be less than the permissible value. So, this is the way how the design processor or design steps are there. Now, let us discuss one example, design example. So, that will make clearly all these steps. So, the first what are the data given to you in this example? Design a footing that is subjected to a vertical load of 70 ton and moment of 23.8 ton meter. The soil characteristics are as follows. So, what is given here? The value of cohesion, which is 0.025 kilogram force per centimeter square, and you know kilogram force per centimeter square means basically you have 100 kPa. So, if I multiply by this this, so you will get 2.5 kPa, 25 kPa, so around 250. So, you get like a 0.0, so the value of cohesion is very small here. Then you have phi equal to 35 degree, gamma unit weight is given, and in addition to this, so here let us clear this. Once you have kilogram force per centimeter square, basically it will be 10 to power minus 4 meter per square. So, that means 10 to power 5 Newton per meter square, that means 100 kPa, right. So, 100, if I multiply by 100, then I get 2.5 only. So, C value is 2.5 kPa. So, very small value. So, C is negligible in this case. So, that means this is not a very large soil. This basically you have the sandy soil only. So, the soil characteristics are saying that these conditions are so same. But beside that, what other data is given? The maximum value of settlement is given 20 mm and tilt is given 1 degree respectively. So, what we do using this data, we start our design. Load settlement curve, this is using from plate load test, and if you see this load settlement curve, this shape of the curve is saying that this is for dense sand basically, and once we say dense sand, then you can consider what is called general shear failure. Otherwise also in this example it is general shear failure. Otherwise also in this example, because phi is greater than 35 degree, so it will be general shear failure rather than local shear failure. So, from the given data we have said that it will be subjected to general shear failure. Now, continue with this, what for the design, assume the trial dimension of the footing as 2 meter into 2 meter square footing at a depth of 1 meter below the ground level. So, the B selected here is 2 meter, basically we have assumed that B equal to 2 meter. Since M and Q is given, so you can calculate the value of eccentricity, and eccentricity is nothing but ratio M by Q. So, this gives you 0.34 meter, and for this 0.34 meter find the value of E by B. So, E by B comes 0.17, okay. And computation of settlement using equations 6a and 6b can be calculated. So, what you have here SE by S naught, and so these equations SE by S naught, this was equation 6a, okay, which we have discussed already in the last lecture. What you need to do, put the value of E by B and get the value of SE by S naught 0.676, same thing for SM by S naught, then you get the value of 0.894. Now, because the ratio of SM by S naught is 0.894, so you can calculate the value of S naught, which is 22.37 mm. Here like you know that one thing need to be observed in this example, that you are getting the value of S naught more than SM. That means though it is acentrically loaded footing, but this is going in another direction. So, this is possible for the eccentric loaded footing, that the settlement of the edge of the footing could be less than the center point. Then what you have, like you have this a settlement which you have find. This settlement is basically for the footing. So, what you can have, corresponding settlement of the plate can be found. So, what is SP? SP is the settlement of the plate. So, settlement of the plate can be found, settlement of plate, and for this you need to use this equation which is for the sand, for the sandy soil. Once you use this equation, then we find the settlement of the plate as 7.53 mm. Now, for this settlement of the plate, what we do, use this chart here. So, if you see the data here, it is 6 and 9, 7.5 will be somewhere here, and if I draw and then I get the value load, corresponding load as approximately it is coming as 2.4. So, this value 2.4 you pick up from here, and so this is the settlement. So, this 2.4 kilogram force per centimeter square is the intensity corresponding to the settlement of the plate. Another way we also find from this load settlement curve using the intersection method. What is done in the intersection method? That you have this curves. So, draw a straight line asymptote here as well as here, and wherever they interact, then we have this their interaction, and corresponding to this point you find the value of this load, which is shown as 20, you have 2.9 kilogram force per centimeter square. Now, in step 4 and A and B, whichever the intensity of the load is less, that should be used for further design. So, the QB is fixed as a 2.4 kilogram force per centimeter square. So, this value will be used for further calculation. Shape of the lead settlement curve indicates there is general shear failure criteria, which we have already discussed. Now, what we do? We find the factor of safety when there is no eccentricity. For E by B equal to 0 and phi by 35 degree, using the chart which we have already discussed earlier and given in the next slide also, these charts, these charts we have already discussed. So, for example, for when E by B equal to 0 and phi equal to 35 degrees, so phi equal to 35 degree will be somewhere here, and E by B will be like here. So, what you get like somewhere in between. So, you will get some value somewhere here. So, what you get the value for n gamma you get is 40, right, n gamma equal to 40. So, 40 will be this will be the value here. Similarly, using other charts also, for 35 degree when E by B equal to 0 you get the values, and the next one here also for 35 degree you will get values using this chart. So, ultimately using these charts what you get, NC equal to 53, NQ 39 and N gamma 40. Using these values NC, NQ and N gamma, we find the bearing this shape factor first before we find the bearing capacity. So, the shape factor for delta gamma is given using this relation, where you put the value of E by B equal to 0 in these equations, and when E by B equal to 0, delta gamma is 0.75. So, even for further calculation you no need to put again the value, because and this will be applicable when B by L equal to, this is the case for square footing, when your footing is square. So, this value can be assumed as a fix for 0.75 for when E by B equal to 0. Delta Q for square footing is 1 and delta C is 1.2. So, these all three shape factors are known. Now, we put in this equation for ultimate bearing capacity and get the answer here. Here all the values are divided by 1000 to get the values in kilogram force per centimeter square, because here 1000 the dimensions of these footings are taken in like so to convert into like yeah 13 this this is like, for example, this is 25. So, it is multiplied by 1000. So, this is, that is why it is getting, instead of 0.025 this so this require a division of 1000. Same is for other factors also. So, what you have the value of ultimate bearing capacity is found as 13.67, and when we divide by this bearing capacity, which you find this bearing capacity 13.67 number is coming using this equation NC, NQ and N gamma. But plate load test is saying that this value should not be more than 2.4. That means, if you are using a value of 2.4 in the design, then you get a factor of safety equal to 5.69 from, and this factor is more than 3. So, this is okay, then you can go ahead with this factor of safety 5.69. Whatever calculation which we have done so far was for E by B equal to 0. Now, for let us have for E by B equal to 0.17 and for phi equal to 35 degree, using the charts you get the NC 31, NQ 31 and gamma 20. Make sure that these values are less than when E by B equal to 0. Okay. It cannot be that they will exceed the values which we have used in earlier. So, again using those equations for the square footing, then you get the delta gamma 0.835 instead of 0.75 used earlier, and again we use the same equation and get the value of QD 9.28, and this value of QD is should need to be less than QD naught. Apply a check. QD naught, if you recall, QD naught was your 13.67, yeah, this was QD naught actually. So, QD naught was 13.67. So, same units kilogram force per centimeter square. So, that means this is okay, this is okay. So, this is reduced. Now, when you have 9.28, then you get for the same factor of safety which we have earlier used, that factor of safety 5.69. Continue with the same factor of safety, we get find the allowable load 1.63 kg per centimeter square, and using this allowable bearing pressure, which is now understand that this bearing pressure has been found with a factor of safety 5.69, and we find the allowable load using this bearing pressure, which is coming 65.22. Though this 65.22 the load ton which you are getting is less than the required 70 ton, but this load is coming with a factor of safety 5.69. If I decrease a factor of safety 5, then this QA allowable load will increase, and certainly this will be more than 70 ton. So, that you can check. That means, because so that is why there is no need to revise the design, even this what you are getting 65.22 ton is less than 70 ton. But if I decrease the factor of safety to 3, then this will be quite higher, even more than 100 tons. So, that is all right, there is no problem. Now, the last step of the design is to find the value of tilt, whether check whether you are in the permissible limit or not. So, for that equation 5 is used. What is using, because Sm minus Se is known to you 0.894, what is this is this value is nothing but S naught, right, and Sm minus these are the ratio Sm by S naught and Se, and this E need to be converted, B is kept in millimeter here and E is also in millimeter, all the numerator and denominator are in millimeter, then finally you get this number for sin t. So, tilt is 0.424 degree, and which is less than 1 degree. So, we can say okay, no problem. So, once you have this if your tilt is within the permissible limit, then it is all right. So, this completes our design procedure. Now, the last part for this dynamic bearing capacity from theory point of view, that is inclined load on a footing. What we have considered so far was an eccentric load acting at some distance from the center, but suppose if you have an inclined load, that means the footing is subjected to a vertical load as well as horizontal thrust, but it is not subjected to moment. So, how to deal? So, here you could see that this is the given problem, and this problem is very practical. This could be some pier or superstructure, vertical load is coming, and this is your footing, right. Now, this footing is subjected to vertical load as well as horizontal. Actually, this is subjected to load R and inclined load R, but this load R, inclined load, is acting at the center. So, if I extend it, it is acting at the center here. Okay. So, the load R can have two components, one is vertical QV, another is QH. So, how to deal in this situation? So, see what will happen when you apply vertical load, no problem, nothing like that, but when you apply the horizontal load, this will try to push this footing like this will try, like suppose this is footing. So, this will try to take away. Now, what will happen? This soil on this side, let us say this is trying to push this side. So, soil this side will come under active zone and the soil this side will come under passive. So, and when you are applying to move it away, the soil this side will try to apply to resist it, which will come under passive pressure, while active pressure will try to no resistance, rather it will be help in movement. Ultimate, and then between footing and below the interface, which is the interface here between footing and soil, what you have here is soil below this. So, there is interface. At the interface you have a friction force, and this friction force will depends on the coefficient of friction between soil and footing. So, ultimately you have one what are the forces which are acting. Total passive resistance which is acting in positive x direction is given by this relation P p equal to half K p gamma h square, and total active pressure is given by this. K p and K a you already know, K p is called coefficient of passive earth pressure and K a is coefficient of active earth pressure. When we say, you can know that they can be linked with the angle of internal friction of phi of the soil, 1 minus sin phi, 1 plus sin phi. This way you can find. Once K p is known, K a is known, K p can be calculated 1 over K a, which can be also directly calculated as 1 plus sin phi divided by 1 minus sin phi, all right. So, this is active earth pressure and passive earth pressure. Then total resistance at the base can be calculated. If you have cohesive soil, then C into area. If cohesion is absent, then this term will be absent, and then mu multiplied by QV, where QV is the vertical load. What is mu? Mu is nothing but here, mu is friction coefficient, coefficient of friction. And once we have all these things, then factor of against sliding can be have, one side you have resisting moment divided by the driving moment. What are the resisting moment? P p plus F, P p is acting in this direction, F is also acting in this direction, minus P a, P a is acting in this direction. These are net, numerator denotes the net resisting force, while the denominator denotes the driving force Q h. So, this will be factor of safety against sliding, and this factor of safety should have, you should have enough factor of safety against sliding. So, now continue with this. The Maheshwari in 1953 and Jambu in 1957 have extended the analysis of bearing capacity for inclined loads, and what they have done, they have find out the the vertical load will be always there. Suppose if you have vertical load only, no inclined load, then the second term on this left hand side NH QH will be 0, right. And on the right hand side, if you see, it is nothing but in Tarjagi theory, or let us say IS code, simply this is QU, ultimate bearing capacity. So, this ultimate bearing capacity is equated with the total load divided by the area, where in case of load some component of the horizontal load is also contributing, and this component is coming through this NH into QH, okay. QH multiplied by NH, where NH is a factor which is given by the Maheshwari using this chart here, depending on the value of phi. So, you could see when 10 phi is from 0 to 1, right, and when phi 10 phi equal to 1, that means phi is equal to 45 degree. So, that means this chart will be applicable when phi is from 0 to 45 degree. So, for these values, as the phi value increases, the value of NH is also increasing, and mind it, this chart is in log scale. Here you have 2, 5, 10. So, the value of NH is varying from almost 1 to when it is 0 it will be 1, it is expected it should be rather that when phi equal to this is 1. So, and then it is going to be around 4 or so. So, we can read the value of NH from this chart and put in this equation, get the on the left hand side and find this. So, this is the one way has been suggested, and not only that, because to counter this they also suggested that there should be some reduction factor for N gamma and NC, which is given in this table. So, what you have in this table? Bearing capacity factor N gamma and NC. So, when you have dF by for different depth of footing, inclination of load with vertical. So, what you have here that 0, 10 degree, 20 degree, 30 degree and 45 degree. So, n gamma will be that these are the factors, that means here these values should be multiplied by these factors and while substituting these values. So, this can be done, but there could be a case when you have an eccentric inclined load on footing, that means you have eccentricity as well as inclined load. That means the footing is subjected to vertical load, moment as well as horizontal thrust. In that case, the last case, third case, so this will be equivalent to an inclined load acting at some eccentricity. So, to deal with this case, the Maheshwari have suggested that we need to use this technique as well as reduce width. That means, first reduce the width of the footing to account for eccentricity, and the Maheshwari have, as we already discussed, the reduced width is simply b dash is b minus 2e. So, first reduce, you reduce the width also, at the same time reduce the bearing capacity according to this method, that means we reduce NC and NQ as well as we have on the left hand side increase. So, as a result, naturally overall what is the conclusion of this both lectures, that when a footing is subjected to eccentric load or a footing is subjected to moment or vertical load, inclined load, then it will decrease its bearing capacity. That means, footings capacity will be less when it is subjected to eccentric load or moment. Okay. So, that this is the conclusion, and as mentioned earlier also, that most of the things including design procedure and example is coming from these references, particularly from the today this lecture is from the second reference, that is a book by Swami Saranji, and that further detail can be found here. So, this completes our on what we call pseudostatic method and a new method which has been proposed by Prakash and Saran. And but so far when we consider the dynamic loads, we have not considered any time variation with the time. We have used seismic load as a static load acting on horizontal direction or moment only, but we have neglected the effect of time. In the next lectures, 2 lectures, we are going to discuss when that these footings are really subjected to dynamic loads which are varying with the time. So, how to deal, and again in that case we will discuss vertically, when the vertical load it is subjected to vertical load only, and in the second case we are going to discuss when it is subjected to horizontal load. So, and with that I thank you very much for your kind attention, and we will continue with the dynamic bearing capacity in the next lecture also. Thanks.